All right, let's get started. Welcome back. This is CS3510. I think this is 14B, and this is just applications of MaxFlow, MinCut. So part of the moral of the NP completeness unit was not that necessarily all these problems were as hard as each other, but the fact that you could solve one problem in a completely random and different way using another problem. And that's kind of what this part is about. There are some problems that seem like they have nothing to do with each other, but then by a description of transforming one problem into another, you could solve them effectively. So we'll just cover three problems today that MaxFlow, the MaxFlow MinCut theorem, any algorithm that uses it that solves maximum flow or minimum cut in a flow network happens to accidentally solve this problem as well. The first one is called edge disjoint paths. So given a graph, a directed graph G, find a maximum set of ST paths where each edge appears at most once in any path. So you don't want just the number of paths, you want the number of edge disjoint paths, in the sense that two paths are edge disjoint if every edge, any edge, appears at most once in any path. So given the paths, none of them share any edge. They're pairwise, the edges are unshared between any of them, right? So here's an example of they need not necessarily be vertex disjoint though, right? So what are some edge disjoint paths in this graph? 1, 2, those are two paths that don't share any edges. In fact, that's all of them because they used every edge. Okay, here's another one though, 1 and then 2. That's a different set of edge disjoint paths, right? How can I solve this problem with MaxFlow? Yeah, make just pretend it's not a graph anymore, it's a flow network, which is just a graph. And label the start and t as appropriately, give everything a capacity of 1. But why does this work? So here's what you do. Take the graph, directed graph, convert it to a flow network with S and T as appropriate. Assign each previously unweighted edge, give it a capacity of 1. Okay? Why do we get the fact, now, then we run MaxFlow on this, okay? Run Ford Fulkerson on this graph. We get a MaxFlow. What does that MaxFlow correspond to, though? Number of paths. Not just paths, but edge disjoint paths. Why? Yeah. Exactly. In the MaxFlow algorithm, recall how residual graphs work, right? You send flow down a certain path, it's gone. That path's bottleneck is saturated. At least one edge every time you run Ford Fulkerson is removed in some sense, right? So when you saturate a path, these edges are marked off. Let's say you choose this path. In the residual graph, those edges can now no longer be chosen, right? They are completely out of consideration. So when you choose a different path, it will not use any of those edges. Therefore, no edge is used in two different paths. So, and for each path, you send exactly 1 unit to T. So the number of units you can send to T is in fact equal to exactly the number of paths that happen to be edge disjoint, right? That's the answer. Now, it's kind of an obvious one because we converted a graph problem to a graph problem. And in fact, this could be probably modified and generalized in some way if you wanted each edge to appear in at most 3 paths. You could have capacity of 3, things like this, right? It's not too hard to generalize this problem. But just kind of a warm-up on how you can solve a completely unrelated graph problem using flow. You just make up the flow, the capacities that you want, and have the flow correspond to something that you hope it does, and you'll end up with the right answer. Question on this one? Okay, the next problem is, it's a graph problem as well, but I'll word it a little differently. Let's suppose you have people and you have jobs to do, like scheduling, like at a company, they have the Trello tasks or whatever, right? Each person can do one job, and each job needs only one person. Can you find the maximum amount of jobs that can be completed, the maximum amount of people-job pairings that can be done in such a way such that every job is done, not necessarily every job, but the maximum amount of jobs that can be done by one person, and the fact that we want to maximize the number of people who are doing jobs, right? One way to think about this, this is not exactly phrased as a graph problem, but it is a graph problem, where you can have the people be represented by vertices over here, and you can have the jobs be represented by vertices over here. It's not necessarily true that they be equal, but then from each edge, for each person, you assign an edge to a job they are capable of doing. That sounds right. Okay. So we can form a graph. Anyone know what the name of that graph is? It's a bipartite graph, okay? This is a bipartite graph. And we are seeking an assignment of people to jobs. No job has 2 people. And hopefully, not every, but a lot of people are working. So we're looking for a maximum kind of situation. But of course, there are situations that may not be possible, right? That you could have something like, right? Not every job can get done. Not every person is going to be working, right? 2 people will be waiting while 1 person is doing the work, right? Does anyone know what this problem is considered in terms of graphs? It's a long shot. It's called a maximum matching in a bipartite graph. A matching is a subset of E, such that no 2 edges share an edge, share a vertex, right? So we're looking for a subset of edges such that no 2 vertices share an edge. This is called a matching problem, right? So we're looking for it to choose a set of vertices, and a set of edges. And really, the set of edges corresponds to who's doing what job, which person is assigned to what job, right? By ensuring that no 2 edges share an end, we are ensuring that no person works 2 jobs. So, for example, these 2 edges could not be in a matching because that person would be working 2 jobs, and that no job is worked by more than 2 people. So these 2 edges could not be in the same job, right? So we want a matching. It's sort of like a loose, disconnected jumble bag of edges, right? How can we solve this with MaxFlow? This is an open-ended question. Yeah.
Add it as an T vertex.
Okay. I'm going to add it here and here.
And then connect all the jobs to T and then all the people to S.
Okay. There's one other thing we need to do, definitely. The notion of maximal matching is not a directed one. So what we need to do is make every edge directed that way. Okay, so we kind of have a flow network here. What's our capacities? On everything, yeah. Okay? So let's suppose we run MaxFlow on this. We need to argue two things. One, the MaxFlow finds a matching. Two, it finds a maximum matching. We need to argue both those things. One, well, first off, just for this specific example to illustrate it, what is a flow? Tell me a flow. The vertices and edges are completely unlabeled, but I'm sure we can find one. Actually, to make things funnier, I'll do this. So this is not the most obvious flow. Because without that, this problem is trivial, actually. So. Start yelling edges at me. This one. This one. Okay. This one? Okay. This one.
Everybody else go straight.
This one? Yeah.
And then the straight ones.
Perfect. Okay. That is a matching. It's actually very difficult to see that. So we need to argue two things. One, the flow corresponds to a matching and it corresponds to a maximal matching. Why does the flow correspond to a matching? The edges, not only is the, so first off, kind of obviously, the number of incoming flow into T or outgoing from S is the number of edges in the matching. But suppose we want the actual matching. We run for Fulkerson and we find a flow. The edges selected in the middle correspond to a specific matching, I claim. Right? If you go back to the undirected graph, and then even further back to the job people assignment. Why does the flow correspond to a matching? Just in the definition of matching, why is it a matching? Yeah.
Well, each job node only has a capacity of 1 to T, so it kind of like ensures that there's only one flowing into each job node.
Exactly, exactly. These two cases are basically impossible. Because we have one outgoing and one incoming from every vertice, we have one incoming to here, right? So of the edge that could be selected here, only one of these could be selected, right? So we have no edge, no vertice is shared by two edges of the matching on the left side. Similarly, because we have only one incoming here, two cannot be incoming here because by conservation only one can be outgoing. So for each vertice here, only two of these could be selected. Right? These we don't care about the matching. That's not part of the matching. That's just a structure to help organize it. So these two edges are never chosen, and these two edges are both never chosen for both things. Therefore, the flow does correspond to some matching. So these never happen by the fact that we did one on each one. Now, let's think about this for a second. Why is it a maximum matching? Yeah.
What does maximum matching mean?
Sorry, the number of edges, right?
Oh, so like the least number of edges that satisfies the...
The most. We want the most number of edges that are also like not touching each other endpoint wise. So we want to say that the flow, the maximum matching is the maximum number of edges that can be chosen in a graph that is still a matching. And again, sometimes that's not good. For example, this graph, again, has exactly a maximum matching of 1, right? So sometimes that's what you get. That's the hand you're dealt. So why is the matching exhibited by the flow maximum? How do you argue something is maximum, by the way? Just in general, like 2050 level question. Yeah, assume to the contrary. Yeah, there's no bigger one. So assume to the contrary, there is a bigger one. Suppose there's some larger matching. If there is a larger matching, what do you know what must be true? It's almost reductive. Sorry? Exactly. That would correspond to a larger flow. Contradicting the fact we found a max flow. And it would contradict the whole Ford-Fulkerson thing that we discovered, right? So if you have found the max flow already, it must be the case that corresponds to the maximum matching, right? If there was a larger matching, suppose there was a larger matching, this larger matching would then correspond, assume to the contrary this larger matching exists, it corresponds to some flow. That matching is exactly, just put that in the graph. That's now a flow. Congrats. But that implies that you found a larger flow than the one you previously found, contradicting its maximality. Contradiction, right? Okay, so you can determine by a maximum matching in a bipartite graph using MaxFlow. Any MaxFlow algorithm off the shelf will solve a little bit of data structure work here. Will solve finding a maximum matching in a bipartite graph. Okay, questions on this example? Okay, both these can be kind of translated as graph problems, and that's less interesting. But let me give you one I think that is probably the most famous example. This is called baseball elimination. So suppose you have a bunch of teams with scores. Let's just be called this for something. You have a certain number of wins, right? And you have a certain number of remaining games to play. And the team wins the season or whatever if they get the most wins, right? Let's say Team A and Team B have 99 wins so far, and they both have one remaining game. Team C has 97 wins and 2 remaining games, okay? So it's possible, some would say it's possible that Team C could tie for first place when what happens? When Team A loses its game, Team B loses its game, and TC wins both its games, right? It's possible for Team C to tie for first by winning both its games and hope that Team A and B lose both their games, right? And suppose there's like 25 other teams here, okay? What's the problem with that logic, though? Is it possible that Team C can qualify for first? Why not?
No sum of addition makes E bigger than A and B.
Suppose we allow a tie for first. Let's say they're happy with tying for first. The one remaining game between A and B could be the case that A and B play each other. If A and B play each other, then one of them will get 100, the other will get 99. Either way, one of them is getting 100. So it doesn't matter if C wins both of its games. Independent of how good C does, the one remaining game, Team A or Team B is going to get a game. We don't know which one, we don't really care. But one of them will get the game, and the highest Team C can get is then tie for second. Let's say A wins, right? Then B gets 99, C wins both of it, it gets 99. The highest C can get then is 99, second place. So what we could say here is Team C is mathematically eliminated, right? But only in the case that the remaining game is between Team A and B. That's kind of the core problem here. And that's exactly what MaxFlow solves in this problem. A game is zero sum in the sense there's always a winner and always a loser. So what you do is you have the flow correspond to games, and then you put them in special vertices whether or not a team wins or not. That's kind of what's going to happen. So what you do is you create a graph of the following form. We'll create a graph, and then we'll solve MaxFlow in the graph, and we'll argue that the MaxFlow corresponds to whether or not a team can be mathematically eliminated or not, right? Many people are interested to know if their team is going to win or lose. This is one idea way to do it, right? a game can be considered like a unit of flow in the sense that it is either won or lost. And if it's won or lost, it goes to different units. So what we do is we create first a layer of the following, of these nodes 1, 2, 1, 3, 1, 4, and let this be the last game. Let's just say it's 3, 4. Let's suppose we only have 4 teams, right? And to each of these vertices, there is a possible pair of teams, right? What we do is we assign a capacity here of, let's say, G1, 2, where Gi, j is equal to the remaining between team I and j, okay? And again, we want to determine if a team is mathematically eliminated, right? Now, of the possible games that Team 1 and Team 2 play, some of those Team 1 are going to win, some of those Team 2 are going to win. So what we do is we create a second layer of nodes here, 1, 2, 3, let's say 4, let's just say 4, right? And T1 is going to win the games that are played between Team 1 and Team 2, some of those Team 1 will win, some of those Team 2 will win, right? So what we do is we assign a capacity here of technically infinity, but it doesn't really matter. You can set it to G1. And we hope to put a flow there of T1 and T2, where T1 is the number of games that Team 1 will win against Team 2, and so on, right? Notice, ideally, by conservation of flow, that T1 plus T2 is going to be equal to G1, 2, right? Of the games played between Team 1 and Team 2, Team 1 is going to win T1 of them, Team 2 is going to win T2 of them, right? Similarly, this is going to go there and there. This is going to go there and there. This is going to go there and there, right? We set this all up accordingly. Then we want to create a capacity that goes along here. What should the capacity be? We want there to exist a flow when the team is eliminated or not, right? So let's think. Fix a team. Let's say we're Team X. Like, this is not for any team. We're specifically Team X, right? We want to determine if another team will eliminate us for each team, right? So the amount that another team can win, the outgoing of this vertices should correspond to what? Sorry? Exactly. But like in a baseball sense, what is that corresponding to?
How many wins they get from each?
Yeah. So T1 is the number of wins they got from this team against team. So the incoming flow to this vertice is the number of wins they get, because it's the number of wins against Team 1, the number of wins against Team 2, against Team 3, against Team 4. It's going to face those teams some number of times. Those are going to flow into here if it wins them, right? So the incoming flow to here is the number of games they could win. So the outgoing flow is the number of games, must be equal to the number of games they could win. So we want to determine if the number of games they could win will beat us. So the way we consider this is we consider the wins of Team X plus the remaining games of Team X. That's the number of wins, that's the maximum number of games Team X can win, okay? If we win, let's just suppose we win all our games, okay? We want to suppose if we do the best that we can, are we eliminated still? So what we do is we consider for each player a graph like this, specifically where this last layer is for Team X. They have a certain number of wins already, right? Let's say Wi or W1 here. So if the capacity exceeds that value, we should consider ourselves eliminated, right? This graph should have a flow only if a team has a path to reach a number of wins that exceeds our own. So you should consider this flow network to have, forget the actual flow itself. Just consider whether or not this network has a flow or doesn't have a flow, right? Is the flow 0 or not? This specific flow network has a positive flow only when we are mathematically eliminated. Team X is mathematically eliminated, right? Any questions on that? Yes?
Why do we need like the remaining X? I thought like WX accounts for that already, as like all of the games.
So WX and RX are specifically for us. Like this first part of the graph sets up conservation of games for everyone, like as the whole system is going to be played out. People are win, people are going to lose, right? Every possible choice of win and losing is going to correspond to a certain flow here, right? We don't want to consider just like how the games are going to play out among each other. We want to determine something specific, which is like, are we going to win or not? Is it possible for us to win or not? And we are eliminated if some other team has a chance to victory, right? So what we do here is we assume that we win all our games. So the number of games we can win is WX plus RX, where WX is the current number of games we've won, RX is the current remaining games. So just assume we won all of those, right? Team 1 currently, we're asking ourselves, can Team 1 exceed us? If they can, then there should be a positive flow on that edge. So they've currently won, let's say, W1 games, right? If they can exceed that capacity, then so this graph should have a flow only when we are eliminated. Did I get that right?
I guess what I was asking is if we win all our games WX, how's their remaining games?
Sorry, say it one more time?
Like if we win all of our games WX, how are their remaining games for us?
No. Wins is current wins.
Oh.
So in this chart here, for example, current wins would be 99, remaining is 2. Yes. Yeah. Okay. So if we have any left over, you're like mid-season, you compute this graph, right? R is remaining. Are you as if you had eliminated, right? So this is a classic example application of MaxFlow. And then of course you do the same for this. But the important part is like it's not really the Ford-Fulkerson part. It's the fact that the definition of the MaxFlow problem constrains for you this situation where team A could face team B. It's a zero-sum thing, right? The flow, the way the flow is defined allows you to correctly formulate this problem in a way that's difficult in any other way, right? If I asked you for an algorithm to solve this problem, it would be a little tedious and non-trivial, because how would you account for the situation when team A faces team B or not, right? But the flow problem makes it a very simple, you can use it as a very simple tool when you need some value to be conserved in such a way, right? And that'll be a classic trick if you see that in the future in any other situation. Are any questions on the baseball elimination problem? Okay.